Assalamu alaikum everybody. This is the second part of the first lecture, and in this we'll be discussing about the computer evolution and different performance measures, and we'll be looking at history of computers very briefly. So let's start. Okay, so the first general purpose electronic digital computer was named ENIAC, Electronic Numerical Integrator and Computer. It was designed and constructed at the University of Pennsylvania, and basically it was a project of US Army. And the important thing is that if you look at it, then you can see that it the weight of this device was 30 tons, and it was occupying 15,000 square feet area. So if you can imagine, we are normally keeping a very high performance computer system today in our pockets. But the problem was at that time that there was no transistor, no electronics, which we have now. So the component used were vacuum tubes, and there were in total 18,000 vacuum tubes were used to made this first computer, the ENIAC. And one more interesting thing is that it consumes 140 kilowatts power, and it could produce 5,000 additions per second. This was the capability of that computer. So this was the first thing. One important aspect was that it was a 10 digit decimal system. So today we now the computer we are using are based on binary number system, but that's ENIAC was decimal number system based. So this was one thing, and they used it till 1955 uh, for their purposes. You can see here that they used it till 1959. Then there was another computer that was produced known as the von Neumann machine, and it was a different type of system, and it introduced the stored program concept. This system was very new, and this concept was also new because before in the ENIAC and other systems they were required to program it by resetting and setting different values in their memory. But if you look at this idea of stored program, which we still use in our systems right today, even that idea to write a program and store it in memory and use it as many times as you want. So this was the idea which was produced at that time. Okay, this system was known as the IS computer, and it had a main memory, which stores both the data and the instructions, an arithmetic logic unit capable of operating on binary data, a control unit which interprets the instruction in memory and causes them to be executed, and finally an input output device which is operated by the control unit. And these are the four basic units which we still see in our computer system. So you can say that this machine was the basis of what we are using nowadays. Look at this diagram. This is the structure of the IAS computer, and you can see on the left side we have main memory. On the right side we have IO equipments, input output equipments, and central processing unit carries the arithmetic logic unit and the program control unit. And these are the basic parts of a computer system. So this machine, the Newman von Neumann machine, has a device which is required to perform the elementary operations of arithmetic, because mostly computers are made to perform mathematics. So addition, subtraction, multiplication and divisions are frequently performed. It is therefore reasonable that it should contain a specialized organ for just these operations, and that we have this arithmetic logic unit for that. Second, the logic control of the device, that is the proper sequencing of its operation, can be the most efficiently carried out by a central program. If the device is to be elastic, that is, as nearly as all purpose, then a distinction must be made between the specific instructions given for and defining a particular problem. So in general, control organs that see to it that these instructions, no matter what they are carried out. So we have a section on the in the middle. We can see the program control unit, CC. So this is the one it is going to perform the central control of the whole system. Third, you can see that a device that is to carry out long and complicated sequence operations must have a considerable memory. Obviously we know that we need to have memory. Even as humans we need to remember a lot of things for our daily work and routine. So this is also very important, and same is the thing with the computer. You need to have a main memory, a memory where the instruction can be stored, and if the code is not arranged, the material must be remembered, and if there are some intermediate results, they are also required to be stored in that part. At any rate, the total memory constitutes the third specific part of the device, that is main memory. The three specifics part, the CA, the CC and M, correspond to associative neurons in the human nervous system. As I said just earlier, that it is just like human brain, and in our brains what we do, we perform the same task. That's arithmetic, we do mathematics, we do logical thinking, and then the brain controls every peripheral of your body, that is hands, eyes, nose, whatever you name it. So these are very important. The device must be able to maintain input output contact with some specific medium of this type. The medium will be called the outside recording medium of the device. You know, our skin, eyes, ears, these are all peripherals which provide input. The skin, through skin you can sense, which is the senses are transferred or propagated to your brain, and brain makes decision. If you hear something, that is also goes to your brain. If you see something, that is the same thing. So, and the fourth part, the device must have organs to transfer information from different parts of a system. These organs are input or output, and you need some kind of peripheral, some kind of equipment which can perform this task for your device, that is the computer. So we can very confidently say that all of today's computers have the same general structure and functions, and thus are referred to as von Neumann machines, with very rare exceptions. Let's we talk about this the memory of IS system, which consists of 1000 locations called words. Every location was called word, and each word of was 40 binary digits, that is 40 bits. Both data instructions are stored there. You can store both data and instructions there. Numbers are represented in binary form, and each instruction is a binary code like we have today. So if you look at the diagram, you can see that the first thing which is shown here is the number word, which is stored in this memory location, and it start with a sign bit. We are going to talk about it later on. So we have 0 bit and 39 bits, that makes it 40 bits. Okay, and if you want to see how instructions are stored, or how instruction pattern, instruction word, you can see that instruction again are of 0 to 39, that is 40 bits, and first 8 bit carries the opcode, the operational code. The next 12 bits carries the address. Third, next 8 bits again the opcode. Next 12 bits again the address. So this is how the instructions are stored. Okay, so the control unit operates the IAS by fetching instructions from the main memory and executing them one at a time. If you look at this diagram, which is visible on your screens, you can see that this is a structure of IAS computer, the von Neumann machine, and I'm going to briefly describe each unit of it, and starting from the control unit and the ALU unit, which is visible right now, you can see that there are some units other than arithmetic logic circuits. There are some accumulators, AC, MQ, MBR. These are basically registers, and remember this, the registers are basically the temporary storage locations. You can store some kind of data for some particular function. You can store that data or information in those registers. So we have multiple registers inside the control unit as well as the arithmetic logic unit. The one which is visible right now on your screen is the arithmetic logic unit. Let's see what MBR, the memory buffer register, does. It contains a word to be stored in memory or sent to the IO unit, or is used to receive a word from memory or a IO unit. It means that data coming from memory to the processor will be stored in MBR, the memory buffer register, and if some data is to be sent to the memory or an IO device, it again is going to be stored in the MBR. So it's an input output kind of register. And if you look at the second part of this diagram, you can see that is the control unit part. You can see that there is in the middle MAR, memory address register, which specifies the address in memory of the word to be written from or read to into the MBR. Remember, we just discussed MBR. MBR was the place where actual data or the code is transferred, which is transferred from memory or an IO device, is received in the MBR, and the address of that data is stored in MAR. So MBR and MAR are the main registers which are handling the data. One is handling the data and the other is handling the addresses of that data, whether it is the address of the memory or a IO device. Then we have on the left side in the middle we can see an IR. IR is again an instruction register, and it's an 8-bit opcode instruction that is being executed is stored in the IR, the instruction register. Okay. Then we have instruction buffer register, the one on the top left side, and it employed to hold temporarily the right hand instruction from a word in memory. So IBR is holding the right side of the instruction from a word in memory. And remember that I have told you about the instruction word, or and you know that first is the opcode, then next 12-bit is the address, then the opcode and the address. So first 20 bits can be called the left side and the other 20 bits called the right side, and this is how it works. Then we have PC. The program counter contains the address of the next instruction pair to be fetched from the memory. Program counter is the one which is going to generate addresses from where the next instruction is to be accessed or picked. Then we have, if you go back to the first part of this diagram, you can see the AC and MQ. AC stands for accumulator and MQ is the multiplier quotient in this particular system, the IAS system. Okay, we have a different name in the microprocessors we use today, but the functions are almost same. So these two employ to hold temporary operands and results of ALU operations. So accumulator is going to hold the data before it is being transferred to the ALU for processing, and the result produced by the ALU will be stored in the accumulator. So the gate to and from accumulator ALU is the accumulator. So in this IAS, the result of multiplying two 40-bit number is an 80-bit number. The most significant 40 bits are stored in the AC and the least significant are stored in the MQ, the multiplier quotient and accumulator. Okay, so IIS operates by repetitively performing an instruction cycle, and that instruction cycle is the one I'm going to discuss a little later. And that instructions, so first we'll see what is an instruction cycle. So instruction cycle means that the data is okay. So instruction cycle is has two parts. The instruction cycle has two parts: the fetch instruction and the execute instruction. So first we'll see what happens during the fetch part of the cycle. The opcode of the next instruction is loaded into IR. We just heard studied about IR. The IR is the instruction register, and the address portion is loaded into MAR, memory address register. This instruction may be taken from IBR, instruction buffer register, or it can be obtained from the memory by loading a word into the MBR, memory buffer register, and then down to the IBR, IR and MAR. The second part is you can see that it's called the execute cycle, and control circuitry interprets the opcode and executes the instruction by sending out the appropriate control signal to cause data to be moved or an operation to be performed by the ALU. And the IIS computer has a total of 21 instructions. This is very few instructions. It's even if you look at today's scientific calculators, there we have hundreds of functions, and each instruction what instruction means, it can be an addition instruction, subtraction, multiplication, division, increment, decrement, and so on. So these are basically classified as instructions. So it had the IIS, the computer which we are discussing right now, had only 21 instructions. If you look at the instructions which IIS had, we had some data transfer instructions like load, store, and other transfer instructions. Then we have unconditional branch instruction. We are going to discuss later about this jump instructions. Then we had some conditional branch which executes when some kind of condition is met, and these are also known as decision making instructions. Then we have these arithmetic instructions, like you can see here, the addition, subtraction, multiplication, division, shift right, shift left, uh, and so on. And finally the address modify instructions, which can be used to modify different addresses. So the thing is that we had very few instructions at that time which a processor can execute, but nowadays we have systems. You can search on Google and you can find out that there are hundreds of instructions which a microprocessor can execute. And the thing which you are looking at right now is called instruction set. So every processor which is produced has its own instruction set, and these instruction sets are compatible. Compatible means like we are using, for example, normally in Pakistan we use this Intel processors normally, mostly, with exception, some exceptions. But the thing is, the software which use some like on i3 systems can also be used with i7 or i9. This is what compatibility means. We are going to discuss about it in details later. Okay, look at this. Some generations of computers. I'm going to just quickly go through it. From 1946 to 57, we had technology used was vacuum tubes, and it was capable of producing something like 40,000 operations per second. In 1958 till 64, transistors were used. Transistor was invented in 1947, and then it was commercially available and used. And transistor is the one thing which has drastically reduced the size of computers and other electronic devices. The miniature devices you see in today is mainly because of this invention of transistor. So anyway, it was capable of producing something like 200,000 operations per second. Then from 65 to 71, it was the new technology, small and medium scale integration was introduced, and you can see that it has increased to 1 million instructions per second. Then from 72 to 77, larger scale integration means that the things are becoming smaller and smaller, the size of the components are becoming smaller. So 10 million. And from 78 to 91, very large VLSI, a very large scale integration of 100 million. And then 91 and no on till now, you can say that we are in the age of ultra large scale integration, with this many operations and more can be performed in today's systems. As I said earlier, that transistor is the one which has transformed electronics. And you can see in this graph that on the left side, transistor was invented in 1947, the first working transistor. Then invention of integrated circuit was happening here, and you can see this increasing the number of instructions or operations performed, and it has reached 100 billions, almost 100 billion by 2011, and it is being continuously upgraded. So the see that you have a technology at your hand which is very, very, very powerful. Okay, let's look at the evolution of Intel microprocessors. And I hope you know this, that Intel produced its first processor in 1971 named 4004, and we'll just look at some main characteristics. Like clock speed, it had like 108 kilohertz, and I'm going to detail it later what is the significance of this clock speed. Then we have bus width of 4 bits. Number of transistors used at that time were 2300 transistors were used in making of this 4004, and it was like 10 size of 10 micrometer, and the accessible memory, the memory which it can use, is 640 bytes, and which compared to our today's standard is very, very small, but like around almost 50 years ago it was a very, very big thing. Anyway, the first uh, uh, after the first microprocessor, Intel produced some other versions, the 8008, 8080, then 8086. This was the first processor which was commercially used in IBM systems and was available for public to use. And the configuration was first introduced with 5 megahertz speed, then 8, and then 10, and it was capable of handling bus 16-bit data. Then it was produced by using 2900 transistors, and the size was very small, and the addressable memory, the one which is important, is the 1 megabyte, so it can access 1 megabyte of memory. Normally nowadays we have systems which with a minimum of 4 gigabytes of memory you have, then it is good enough for today's handling of today's softwares and all that. Anyway, if you carry on, you can see that these characteristics, I'm going to identify few: the clock speed, the bus, and the addressable memory. These are important factors, and you can see that with the passage of time, in they produced this 8088, then 80286 with 16-bit and the speed of 12.5 megahertz, then addressable memory of 16 megabyte, which has increased from 1 megabyte. And you also see this virtual memory which was 1 gigabyte at that time. So virtual memory, we are going to talk in detail about this virtual memory concept. Anyway, so if you look at 386, the next system, 386 SX and DX, you can see here that it was able to access 4 gigabytes of memory, the TX version, and the SX version was able to handle 16 megabytes. And then the 486 system, which was again of 32 bits, you can see 32 bits, and with 50 megahertz speeds. The speed is increasing, the size of the bus or the data size is increasing, and with that the addressable memory. And you can see by when the 486 was launched, we had another type of memory which is now commonly used. It's called cache memory, and that was also introduced with 486, and it had only 8 KB of cache memory. We are going to discuss about cache memory in detail later on. Then look at this, the Pentiums, the Pentium 1, the Pentium 2, and Pentium 4 is 64 bits with accessible addressable memory of 64 GB and virtual memory of 64 terabytes and cache memory of 512 KB. and there was new concept of level 1 and level 2 caches. I'm just taking the name of these terminologies just to make you familiar with the terms, and then we are going to discuss all about these terminologies in detail in our later sessions. So then Pentium 3, Pentium 4, Core 2 Duo, and i7. If you took a look at i7, you can see that i7 is of 64 bits and it's operating at 3.5 gigahertz with 64 GB memory, addressable memory, 64 terabytes of virtual memory, and 1.5 megabytes of what? The cache. 1.5 megabytes of cache memory. Okay, so that was about the general purpose computers, but if you look at the market of computers, it is not limited to only general purpose. There are embedded in devices, like if you can see that in the automotive market, we have ignition system, engine control, brake control, and automatic cars. Then consumer electronics, you can see find microprocessors and computers basically in all of these devices, uh, like television, the toys, the telephone, the cameras, everything. And then industrial control, robotics and control system for manufacturing, and sensoring, medical, you can see the infusion pumps, the dialysis machine, the cardiac monitors and other devices. And of course in the office automation, you can see that you can find these devices in your fax machine, photocopy, printer, monitor, anything, you name it. So its market is very vast. If you briefly talk about the embedded systems, so embedded systems have mainly a processor with memory and some software in it, and it can have human interface, AD conversions, sensors, actuators, DA converters, diagnostic ports, and auxiliary systems for power and cooling, and some external environment which is sending and receiving data, and maybe operating some other mechanical devices. So this is the basic architecture, basic design. Okay, so this was the brief about history of computers and its evolution, and some main terminologies which you need to know. And in the next session we are going to continue this topic, and if you have any questions you can ask and send me the query. I will be more than happy to answer all of your queries, but you need to be very specific in your question. Okay, and you need to just focus on your studies. That will help you a lot. Okay, that's it for this session. Thank you very much, and Allah Hafiz.